Okay, so we talked about the need to localize an object, and we talked about the fact that we need wave solutions to describe a particle. So we need a wave that describes a localized particle. So here is our particle that lives in the one-dimensional universe. Let's call it the x direction, and let's say that we allow it to live between 0, so this is x equals 0, and this is x equals L. Okay, so it can live in there, and we want waves to describe this particle, and waves are sort of slippery kinds of things. We're not terribly familiar with the way they behave, and so what we want is to put in the strongest conditions to force the particle to live in this region. So we're going to introduce an infinite force, and so we want to ensure at all costs that the particle stays in that region. Now we know that the force is equal to minus the gradient of the potential, and so the way to accomplish this is to have a potential which is infinite. Right, so the potential is infinite for x less than 0 and for x greater than L. Okay, and then it's going to be 0 for the other region, which is what's left is the region between 0 and L. And so we'll have the particle be free in that region. Okay, so let's sort of make sure that this is making sense, right? We know that F is equal to minus the gradient of the potential. Sorry, I should have just written this as U, since I use U for the potential, not V. And so we're in a one-dimensional universe, and if we're dealing with x, y, and z coordinates, as we should be, then this would become minus d by dx of the u function, and that would produce a vector that looks like that. Okay, so what does this look like at x equals L? Well, at x equals L, we are dealing with minus, right, we're approaching, we're thinking of this as a limit, and so we're it's a tiny little, it's an infinitesimal distance x, and so we have an infinitesimal quantity here, but it's highly discontinuous. So we're going from f, for the potential function, which is just to the right, and just to the left, it shifts by an infinite amount. I mean, this is highly non-physical, but it makes things easier. And then we'll later on in the semester we'll sort of think of this as we'll think of more realistic ways to produce potential that's continuous. It doesn't have these kinds of discontinuities. So here we're going basically from infinity to 0, and so over an infinitesimal region, we have infinity minus 0, and of course that's minus infinity overall, and we have an I hat here. And so we get an infinite force that over here pushes the particle to the left, forces it to the left, and at x equals 0, we have exactly the opposite, right? We have minus, it's now 0 is the potential at 0, at x equals 0, and just to the left of that, we have infinity. And so when we divide that by epsilon, we get a minus times a minus, that's a plus infinity. And so there's an infinite force pushing the particle to the right as it approaches x equals 0. Okay, so that seems like that accomplishes what we need, and now we want to find the solutions. What's the behavior of this part? What's the wave function? Okay, so let's go to the time-independent Schrodinger equation, right? So there's a kinetic term, Right, so it looks like that, and then the potential is 0 in the region that we're considering, where the particle can live, and this is equal to E times the function. So we'll put an index here, indicating that there could be different solutions or different values of the energy. The particle could have different energies. We're going to determine what their values are. So we write this as two derivatives in psi, and that's equal to minus 2m times the energy over h bar squared times the spatial part of the wave function, psi n. We'll just call it the wave function. And notice that this equation tells us the behavior of psi, tells us about the bending of the wave function. So it's basically telling us that if this is x, and this is 0, and maybe this is L, then the wave function in here, right, so if in places where the wave function is positive, so it has some value up here, this equation is telling us that the second derivative, the way the wave function bends, is negative, because the function itself is positive, has some value up here, and so the bending has to be toward the axis, something like that. Whereas if the function, if we're down here, right, we're not going to be here because the function has to be smooth and can't have multiple values for, multiple different values for the same point. So we have to move over here or over there. But say we're here and the function is negative, then this equation says that the second derivative is positive because this is negative and this is negative. We get a positive value. So the bending down here has to be towards the upwards direction. And so you can see that the bending is always towards the axis. So these are possible solutions. Solutions can look something like that. Well, we know what this looks like. And of course, these things have to come to 0 at 0 and L. So that could be a solution, something like that. Or actually, we will have to be more careful to see that it respects certain symmetry properties. But this is telling us that sines and cosines are the solution. And so a general psi of n can be written in terms of a times, say, sine and cosine, the sum of sine and cosine terms. And this term here, we end up getting the square root of this quantity. So it's 2m en over h bar squared square root times x. So a term that looks like that with undetermined a coefficient plus b times the cosine of this kind of thing. So square root ends there times x, so it's something like that. And then we impose our boundary conditions, so psi of x equals 0. At x equals 0, the thing becomes 0, and we have b cosine of 0, which is just b, but this has to be 0 because the function has to be 0 at x equals 0, so that tells us that b is 0, and the cosine term disappears. And the other boundary condition, which is the same as that one, is that the function at x equals L, which is, so this has disappeared. All we have is this one that tells us that this 2m en over h bar squared square root times L, this must be equal to 0. And so this quantity in here, so this could have different values, right? The energy can have different values, but this whole quantity has to make the sign 0, and so that imposes on this quantity times L can be a multiple of pi, right? Pi, 2 pi, 3 pi, and so on, so n pi, because that makes this whole thing, makes the sign of that equal to 0. And so this tells us that, right, we want to solve for the energy. Let's square it to, 2m En over h bar squared times L squared is equal to n squared pi squared. And this tells us that the energy, En, has these possible values. We could simplify with pi's, and the h bar has a pi in it, so we could simplify that, but let's just leave it as it is. We divide by 2m L squared, and so we get from our boundary conditions that the energy has discrete values, right? So n can be equal to 1. So we have pi squared, h bar squared over 2ml squared, n can be equal to 2, and then this ends up being 4, and so it has specific values, and that's because specific values of this function allow it to obey the boundary conditions. Or we can only fit waves into this region in specific ways.